Hey, hi everybody. Welcome to the first LEAP lecture of the fall semester. We're happy to have David Hogg here presenting today, and I'm going to hand it over to Joe for an introduction.
Yeah, hi. So welcome to another LEAP seminar. So today we have a local guest, David Hogg, who is a professor of physics and data science at NYU, also a senior research scientist at the Flatiron Institute and an affiliate of MPI. So his research interests span many topics, seeing his website, being observational cosmology, statistical inference, amongst many others. And yeah, today he's going to be talking about machine learning for science with his provocative title. So very interested to hear what you have to say. Take the floor.
Good. Do I need to say anything about this? No. Oh, one thing I want to say is almost everything I do in machine learning is with Soledad Villar, who's a mathematician at Johns Hopkins and works on the mathematical basis for machine learning.
Is your mic pack
Oh, my
on?
mic's not on. I think I do that. Now my mic's on. We're good. Now I can talk to the room. Now, like, hello. Yeah, good. Anyway, so everything I'm going to talk about has some connection to Soledad Villar because she is my machine learning collaborator and she works on the fundamental basis of machine learning and works on her papers have proofs in them, which makes me uncomfortable. I never do anything with proofs. But anyway, so I will sort of point out occasional moments where we're actually talking about something that's really mathematically accurate. Sometimes I'm really just talking about the practice of science. And a lot of it will be about the practice of science. Okay, good. So this is the summary of my talk. I'm going to say some negative things about machine learning, and one of them is going to be kind of about trust, and one of them is going to kind of be about biases. And I'm going to bring up some biases that come up when you use machine learning methods. But I'm also going to say a lot of positive things. One is that when you're doing big science projects, you usually need to use machine learning at some level these days because of the scale of the problems we work on, the engineering scale. And I'm going to also say that machine learning has some intellectual benefits when you're doing causal separations. If your data are kind of being affected by multiple things, sometimes machine learning can help you. And I'm going to make that fairly precise in the talk, not exceedingly precise, but fairly precise. Hello. Oh, that's my fault. Okay, good. So I wanted to start off by saying, like, where has machine learning given us transformative new results in science? And Vivi knows this joke. It hasn't yet. Machine learning has been a useful tool in various places, but we are still waiting for the killer app where machine learning actually makes a really big impact. And we're working to find that in astrophysics. And I think a lot of you here are working to find that in the earth sciences. By the way, who here works in earth sciences in general? Most of you. Good. Okay, great. Because I will say some earth science related things eventually. Now, when I say that, when I give that slide, people say, but machine learning solved protein folding. And I just want to push back on that idea a bit. But, there's this project AlphaFold. I think there's several things that have been very impressive that have come out of the big machine learning companies. One of them is AlphaGo, where it plays Go very well. That's very impressive. AlphaFold, which is the thing that finds protein folding. And then there's another related project, AlphaFold, that found new inorganic crystal structures. These projects are very impressive, and AlphaFold is a particularly impressive one because you can put in a sequence and it will tell you what kind of protein what structure of protein you'll get out of that sequence. It has tons of clinical value, this project, but we didn't learn anything about how proteins fold. None of the physics of protein folding was aided by that, because in fact it replaced a physical model with an effective machine learning model. So it actually is kind of almost against the idea of learning something. Now, I don't want to sound so negative. That sounds very negative. I don't want to sound so negative because I do lots of engineering. So you don't know much about astrophysics, but astrophysics is a big engineering operation these days. We do big, coherent global projects. You might hear about, James Webb Space Telescope or or the Sloan Digital Sky Survey. We do very big projects that involve many institutions and many partners. And there's no little labs anymore. Well, there are some, but there are very few little labs left in astrophysics. And that means we do big engineering for big projects. And I love engineering. That's one of the main things I do. And so one of the reasons we're interested in machine learning in my group, and I've been working on machine learning since back before it was cool, is because we do big engineering projects. And so let me just, and so I'm going to come back to, actually that theme of engineering is going to keep coming back. And by the way, you can think about this AlphaFold problem as kind of an engineering problem because if you are looking for a protein that has a certain conformation, this can tell you what sequences might make that conformation. So you can see how this could be inserted at a clinical level or an engineering level into a project. Actually, whenever I say engineering, you can also translate to clinical if you want, in the sense that it's where things are pragmatic or practical. Okay, so I wanted to define machine learning. So Soledad Villar and I put out a paper with more or less the same title as the title of this talk. We got tons of email back. And one difference between an astronomer and a mathematician is that when you put a paper on the archive and people start sending you email, the astronomer is like, cool. And the mathematician is like, oh no. Basically, you never get good feedback if you're a mathematician. It's just like your proof is wrong. But we got tons of feedback when we put this out on the internet. And most of the feedback, oddly, was not about whether machine learning was good or bad for science. It was about this. It was about what is the definition of machine learning. It turns out nobody agrees. Now, we got tons of feedback saying our definition is terrible, but nobody gave us an alternative definition. So this is my definition. I'm sticking with it. Actually, one person did give us an alternative definition. The alternative definition, which sounds like a joke, but I'm not sure is actually, is that machine learning is statistics when it's done in a computer science department. Which sounds like a joke, but actually it's not very far off from being correct. But anyway, for me, a machine learning method is a method whose capability improves as it sees more data. And I mean substantially improves. And actually, when I gave this talk in front of statisticians, they got really mad about this sentence. So it's very hard to say something that isn't controversial here. But then the weird thing about it is then there's no definition of machine learning. Like machine learning, you know it when you see it. Like that, I don't know. Anyway, if you take this attitude that it's something whose capability improves as it sees more data, then a lot of classic things that you might think are boring are actually machine learning. Principal components analysis is machine learning. Independent components analysis. Linear regression is machine learning because you can get, as you get bigger and bigger data sets, you can put more features into your linear regression. Gaussian processes are, I'm told you people call that kriging. I don't know, I think that's over, right? Everyone calls it Gaussian process now. Anyway, but of course it does cover all the contemporary things like transformers and CNNs and stuff like that. Anyway, that's my definition of machine learning. And actually, a lot of the examples I'm going to give you in this talk are really in this classic category, because I still love those old methods. PCA, linear regression, they're very powerful methods. They do a lot of great things. We've succeeded in a lot of tasks with those methods. So, whenever I have a student who wants to do like a transformer, I'm like, start with nearest neighbors and just see if you can beat it. And often we never beat nearest neighbors. We just put out a big catalog of quasars, an all-sky catalog of quasars, and we tried so many machine learning methods, and the nearest neighbors beat them all. And so it's just done with nearest neighbors, the project we did. Good, and you all know this because this is like a machine learning group in here. Actually, by the way, who here would say that they don't work on machine learning? Oh, a few of you don't. Congratulations. I respect your life choices. But I think everyone now in the world now understands what supervised machine learning is. But just very quickly, you have a training set. And in that training set, you try to find using that training set, you try to find a function that does a good job of predicting some labels for that training set. And that function is in a big space, and people talk about the weights. Training is like setting the weights. Those weights are like the parameters of a very big function. And then at the test step or the prediction step, or sometimes people call it inference, which makes me upset, you predict new labels for new data points that weren't in your training set. That's the classic supervised machine learning. I think there's lots of things going on in this building and this university that fall into this class. And I'm mainly going to be talking about that class. There's a lot of ways you can use machine learning. I wrote astrophysics here because that's where I use machine learning. But I'm really going to focus on the regression and emulation. So regression is when you're trying to label a lot of objects. And then emulation is when, what I call emulation, sometimes people call surrogate models. I don't actually know what the terminology is in neurosciences, but what I'll call emulators are things where you've trained a machine learning model to replace your simulation. There's some expensive simulation you're doing of the oceans. It's too expensive to do lots of them. So you do as many as you can. Then you train a machine learning method like a regression to reproduce what that very expensive simulation would have done. I'm going to call that emulation. That is going to come under attack in this talk, I'm afraid. I'm going to be a bit mean. By the way, one thing that earth science and cosmology have in common is that we both are capable of using all of the computing resources of the United States. And that sounds like an exaggeration, but it's literally not. If astrophysics was given the entire compute resources of the United States, we'd use it flat out full time. We would have no trouble. Every single project I'm involved in is compute limited. And like compute limited by like factors of hundreds, not compute limited by like, oh, we need a few more computers. And I think that's true for oceans too, right? And atmospheres. And
use the GPUs.
Yes, we would use all the GPUs too, yes. Actually, the big thing that's happening, of course, in all of our work is that we're moving everything we can to GPUs. Luckily, I mean, one of the computational situation has changed so much even in the last 2 years, because now it's so easy to deploy on all different hardware. When I was a kid, even when I was a kid, just a few years ago, it was actually quite hard to deploy on lots of different hardware. Now it's very easy. That, by the way, forget all the machine learning stuff. The most valuable thing the machine learning community has done is produced all these tools that abstract away the hardware. That's been incredible. Whatever you're doing, you can use those tools. Even if you're doing classic simulations of the ocean, you can use the machine learning tools that abstract away the hardware. So some of my colleagues see machine learning as just a way to trick people into building really good low-level tools. And that's a perfectly good use of the machine learning community. I like it. So we use it at all levels, the machine learning tools now. So just to make clear or to sort of emphasize what you get, if you follow what my definition of machine learning, that original definition, it's something where as it sees more data, it grows more capacity. You generally end up in a box, a philosophical box. And we're going to do a little philosophy here. You may not have thought about these words since college. Maybe you never even saw these words in college. But there's the concept of ontology is the study of what exists. And in machine learning, the only thing that exists is the data. There's nothing else. You see everything as a relationship between data and data. You have training data and you have test data. And as long as you do a good job of predicting the labels, which are also data, from your training data, so this data to data transformation, as long as you're doing that well, you're good. There's no other consideration in machine learning except, are you doing well with the data? And then of course, I'm talking mainly about regressions here, but you could talk about density estimation or dimensionality reduction, or whatever you're doing. You're really just asking, can we do a better job of explaining the data or describing the data? And similarly, there's an epistemology. How do you know what's true? Epistemology is the study of like knowledge. How do you know whether you have a good model, a true model? Well, it's a good model if it performs well on the data, and a worse model if it performs worse. Really, the only consideration about a machine learning model is it doing well? And when you criticize a machine learning model, it's because you can find data on which it does poorly. And so it's very interesting to compare these things to, say, physics. Like, I'm a physicist, I'm a classical physicist. Like, I'm literally a classical physicist in the sense that I work on classical physics. And in classical physics, all of the things that are relevant the data are the least important thing. In fact, usually the theory is related to the data through some abstraction, right? And we work on like the metric of space-time. And everything, we care deeply about the latent structure of the model. It has to like obey symmetries and like gauge invariance and unitarity and things like that. And we judge things as being true on a huge set of considerations that go beyond the data. Like, does it fit in with other things we believe? Is it time invariant? All sorts of things that go way beyond the data themselves. By the way, this is another point. When I give this talk in front of physicists, they often object to that point. Many physicists say, no, the only purpose of physics is to explain the data. And I don't think that's true at all. For instance, the solar system can be explained very beautifully with a post-Newtonian calculation, but we don't believe that the laws of physics are Newtonian anymore. We aren't driven really by the data for that change. We're driven by like things like simplicity and beauty of the latent structure or whatever. So I just disagree with the physicists on that one.
First statement reminds me of Wittgenstein's first line in Tractatus. The world is everything that is the case. Oh, sorry. I said it reminds me of the first line of Wittgenstein's Tractatus, which is the world is everything that is the case.
There's a quotation from Wittgenstein in the room, which makes me very pleased because Wittgenstein was my favorite of all the philosophers when I studied philosophy in college. Actually, Wittgenstein is interesting to read in this context because Wittgenstein thought a lot about the structure, more like the structure of communication than the structure of knowledge, but it's very relevant to science. Like, what are these latent things? Good. This is just a random comment, which I shouldn't even make because it's just aggressive. But I love interdisciplinarity. I founded the NYU Center for Data Science with other people at NYU, including the famous Jan LeCun. We started the Center for Data Science, and we did it specifically to build an interdisciplinary effort. And this is an interdisciplinary effort. It's great. I love it. I'm all for it. But it is a little bit of weird in the interdisciplinarity of machine learning, because the interdisciplinarity of machine learning is really an interdisciplinarity with huge tech companies. And they really have very different goals from us. In fact, some might say very badly misaligned goals with us. And that's an interesting issue when we think about using their tools. But swords can be beaten into plowshares. But I have to say, the things that the machine learning companies do is very impressive. Like, I'm really impressed with TikTok, I have to say. It's just very impressive how quickly it understands you. Good. I'm saying the things over and over again. I can move on. I'm just saying that machine learning is kind of trying to reproduce what it's already seen, whereas in science, we're usually trying to find something new. Maybe that's less true in different disciplines, depends on your discipline, but in astrophysics, we're very much about discovery. We want to discover things people haven't seen before. So in astrophysics, we're always looking to higher redshifts, earlier times, younger things, older things, whatever than have ever been found before. So actually, these sort of machine learning methods don't always help us. Good. Now I'm going to talk about trust, and trust is now going to thread through my talk, because the challenge when you're using machine learning is, how do you trust it? Since you don't really understand what it's doing internally, you build some big transformer, like what's it doing? And I believe you can't know, you literally cannot ever know what it's doing internally. But this is controversial. Certainly some people push back on me when I say this, so I'm not going to commit hard to that. But it is interesting, we spend a lot of time looking at the brain, and you still can't look at somebody's brain and tell what they know and what they don't know. And similarly, you can look inside the weights of these machine learning methods, and you don't really know by looking at the weights what's going on. And interpretability, I'm very negative on interpretability. I don't think it's worked out very well. However, it is interesting that machine learning methods can be interrogated. By the way, how do I know that somebody knows something? I don't know it by looking inside their brain. I know it by chatting with them. And in some sense, one of the things that interpretability is moving over to is more like an interrogation thing where you interrogate the model. And that's interesting. But there are definitely trust issues. This is very different from a numerical simulation. When you have a numerical simulation, if you've written it correctly, you have a set of unit tests. And if it passes its unit tests, you know that in some limit, it actually computes the solution to the equation that you actually care about. That's never true for any of these machine learning models. You never have those kinds of guarantees. So I asked this question, where in science can you use a model that you don't understand? And I don't think I answer it right here. No, I don't. The weird thing is I'm gonna answer this question all the time. We use model things we don't understand all the time in science. And I work on imaging a lot, so I work with imaging detectors, and I'm gonna bring that up in a minute. There's a lot of things that we don't understand. And this is an example in astrophysics. This is a really out-of-date example. I just have it because they made a nice, simple picture. This is not my work at all. But this is the kind of thing that astronomers are interested in. This is an n-body simulation of a huge chunk of the universe. These n-body simulations are outrageously expensive. They have many different categories and resolutions and different amounts of physics. They're multi-physics, multi-scale, if you've been putting in grant proposals. They're all those things. And they're extremely expensive. A simulation like this, for a big chunk of the universe, a simulation like this will take weeks on 100,000 cores. So these are like very expensive operations. And this is a prediction that's a trained machine learning model that ran in, I don't know, a few milliseconds, that was trained to reproduce these kinds of simulations. And this got cosmology. One of the reasons I'm showing you this old paper is this got cosmologists very excited. Like, could we be working with this? Because this is very easy to compute. This is very hard to compute. And a lot of the statistics are the same here. And we mainly care about the statistics. By the way, cosmology, the weird thing about cosmology, like in earth science, like you actually care about like the Atlantic Ocean and the Pacific Ocean and certain things that happen on the Earth. In cosmology, every part of the universe is considered to be identical. And so we only care about statistical properties. So if you can get them right, you're good. So that's one of the reasons why this is very promising in cosmology. But whenever I see pictures like this, I think of pictures like this. This is also ancient. Look at this. Ancient history. Half of you weren't even born in 2015. That was me. Phew. This is a very famous example, but I just want to walk through it because it's so important to this question of trust. So this is a picture which in the state of the art in 2015, this paper, by the way, this paper launched so many papers. There was a few papers in 2015, and now the word adversarial is in something like 2,000 papers a year. Like the word adversarial is bigger than all of astrophysics. But anyway, this is a picture which state of the art in 2015 was classified as Panda at 57.7% confidence by whatever state of the art was. Don't remember the details. Then they did a lot of work. This is a white box attack, so they can look inside the machine learning model. Looking inside the machine learning model, they found this very carefully tuned bit of noise. They added it at this amplitude to this image, and they got that image. They got this image, same classifier. It says it's a gibbon at extremely high confidence. Say again.
I think you have to know the model, though, to do that, right?
Yes, this is white box. Actually, the more interesting attacks are black box, because right now people are trying to figure out if you can like wear a certain shirt and it causes a Tesla to crash. Like I love that project. I would totally work on that in a different life. But anyway, those black box is way harder. This is actually very easy to do. If you have an emulator that you're running in the ocean or whatever, you could do this in an afternoon. It's a very easy thing to do. And this paper tells you how to do it. It's very simple. And there's actually many ways to do it. This gives you just one example. There's many actually ways to do this, and it's fun.
When you say to do it, you mean to find what kind of adversarial attacks are successful.
Exactly, yes. Exactly. And this paper is a classification, so you have to adjust it to regression, because most people here are doing regressions, not classifications. So you have to make the adjustment. But it is straightforward. Yes, thank you for that question. Good. Now, first of all, usually when I give this talk, everyone's searching on their phone for what a gibbon looks like. Do you know why this looks where the gibbon is? Can you see the gibbon? I can see the gibbon now because I've spent so much time poring over this example. This looks like a gibbon. That gibbon's face is a little black patch. But somehow this changes the attention of the model to there and says it's a gibbon. Anyway, this shows you, since I can't see the difference between this image and this image at all, this shows you that the machine learning method is not doing what you're doing. Well, maybe you actually, maybe people do are like, totally, that's a given. I think this is the panda, and I think that's a panda. And this shows you that it's not doing what you think it's doing, which has implications for this, because if you're going to put, if you're going to put this into a scientific project, you better be sure that it's doing what you think it's doing. Good. That's the kind of my trust point. And adversary, some people think the adversarial attack thing is stupid because it's a set of measure zero. Like you'll never happen to see this noise in the real world, so it doesn't matter. It's a set of measure zero. Forget about it. But I think it's revealing that the model isn't doing what you think it's doing. Certainly not doing what you're doing. And I think that's scary. So I believe that this kind of problem leads to a kind of confirmation bias or amplifies the confirmation bias. So now getting really real world. Let's just get super real world for a second. Real world, you've done some big experiment. You learned something important about the oceans. You used your emulators. You had to use your emulators because you couldn't do enough simulations of the ocean, but so you did it with emulators. Now you either found something really boring about the oceans or you found something really exciting about the oceans. If you found something boring about the oceans, you're not going to further investigate because you're going to be like, cool, well, it confirms what we already know about the oceans. But if you find something really exciting about the oceans, then you're faced with a confirmation problem that you can't afford. You can't afford, by construction, you can't afford to do the simulations you need to do to check. And so that situation leads to some very bad confirmation bias or amplifies. When I gave this to statisticians are like, confirmation bias always exists. There's nothing new here. And I'm like, okay, fine. It's not really new, except it's amplified because you've gotten yourself into a situation where you can't do confirming experiments. You can't afford it. Like we're moving into a region of cosmology and earth science where we're making results that we can't confirm, which is weird. Don't have a solution. So I want to make another that was kind of a real worldy. Let's make a really technical point. Blah, blah, blah. Let me give you, I'm going to walk through this picture. Sorry, this picture is so tiny. I apologize for its tininess. I should have made this 4 slides. This is completely fake data. Okay. I'm God. And this is an astrophysics example, but I think you'll understand what I'm saying. But this is a perfectly fake data example. I'm God, so I understand everything about this problem perfectly. I built this whole problem. So this is a set of data, which you can think of as like spectra. We took spectra of a bunch of objects, and those objects have ages, and this spectrum has an age of 1.2, and this spectrum has an age of 6.1, and this is 5.0, and I have tons of these. Actually, I have more than 100,000 of them. But only some of them have labels. Only 4,096 in my training set have labels. And this is a picture of my training set. This is that age that's written here. This is the label. And this is some other parameter. I'm just plotting some other parameter so that you can see there's a trend in the data. Age is related to radius. This is very astronomical. This is what astronomers care about. Where are the stars in the galaxy and what are their ages? This is like astronomer land. So we have age here, which is encoded in the spectra. We have this other parameter, radius, and you can see there's a training set of dots. That's that scary set of dots there. And then what you can't see here is there's both red dots and squares. They land right on top of each other. The red dots is the true relationship in the data. Remember, I'm God. And the black points are the means of the training labels in the bins. My training set is perfectly unbiased. It's a beautiful, unbiased sample. Good? Second, I validate. Here's a validation set. There's a validation set. I have 48 more with labels, and I can validate, and you can see that x equals y. My method is doing okay. This is like regression estimated label versus true label, and it's looking nice. Although if you squint, you might be a little concerned. Astronomers might be a little concerned. Now, the crazy thing is, I used a multi-layer perceptron here with a ReLU activation function. If that doesn't mean anything to you, good. I used a ReLU activation, and this data set was made with a ReLU activation. It's linear with a ReLU activation. So literally, my data were generated within the model space of the multi-layer perceptron. So there isn't even model specification issues. My data are perfectly consistent with the mean properties of the universe. My true theory is in the space of the machine learning theory. Like, you don't have to worry about any universality here. We're dead in the model space. You got it? Perfect. Couldn't be better. No one's ever been in this situation, by the way, in the history of humanity, because you've never had a representative training set and you've never had your model inside the model space. But whatever, we have that now. And now I apply it to a test set, which is very large, and so that I can get ages for all these other stars. The idea is in astronomy, you have 4,000 stars that many graduate students died to bring you these ages. And now you want to apply those ages to a much larger set of stars, and this is what we've done. And notice the x's here is the relationship we got at the end of the day. And notice it's biased away from the true relationship. And that bias might look small, but that bias is 30 sigma because I have 100,000 objects. It's a 30 sigma bias. Perfect training set, perfectly. Oh, by the way, the test set were drawn from exactly the same distribution as the training set also. Remember, I'm God. I did it all correctly. And yet you get this bias. So these ages are bad. And as an astronomer, if I had just used my training set to tell you what the relationship was, I would have gotten a better answer. I add 100,000 new points and my answer gets worse, not better. See?
Does it mean it's not machine learning? According to your own definition.
Oh, good question. No, it is still machine learning according to my definition, because actually, if I increase the training set, this is a sandbox, by the way, that's open source. It's all sitting on GitHub, so you can play with it. And in the sandbox, if you increase the number of training points, the bias gets smaller. It works. Machine learning does work. But in general, you're in this kind of situation where you're using the machine learning because you have expensive labels that you want to broadcast. Good. Just a little warning. By the way, when I talk to astronomers, I open with this example, and then everyone spends the rest of the talk on their phones, like texting their graduate students, because literally this is the only way in astronomy we know the ages of stars. We have a few stars that we know ages for, and all the rest has been gotten from machine learning. This is literally the only way we have stellar ages. Horrible. I don't have a solution for this problem. I am doing some work on machine learning methods that produce likelihood functions and then maximize the likelihood functions that have some hope of overcoming this bias. But right now, we don't have a solution for this. By the way, linear regression doesn't have this problem. If you use linear regression, you get an unbiased estimator. It really is the complexity of the regression that does it. You gonna ask me something?
The noise distribution, that wasn't generated by the MLP. That's just sort of added on to whatever the MLP is doing.
Yes, there's some Gaussian noise both in the X vectors and in the labels. But this doesn't come from the label noise, because I turned the label noise down to 0 and I still get this effect. But there is Gaussian noise floating, yeah. Because again, for us, there always is Gaussian noise. Well, there's often other kinds of noise as well, but there's at least the Gaussian noise. Good. Here, I've promised you I'd come back to this question, where can you use a model that you don't understand? And I would say in science, we use instruments we don't understand all the time. I work in imaging, and we do a lot of stuff with infrared detectors. Infrared detectors are literally not understood, and they've been developed by big military organizations. By the way, astronomy is a big partnership with the military. You may or may not know that. I assume earth science also is at some level, in the sense that almost all of our instrumentation has military origins. So we use these infrared detectors that were developed by the military, and even the military doesn't understand how they work. And they have a lot more money to figure out how they work than we do. So we are using infrared detectors like the ones on James Webb Space Telescope that I mentioned earlier. Those were built by military contractors. They have issues that we don't understand, nobody understands, and we can use them to make very precise measurements. In fact, the James Webb Space Telescope is currently making extremely precise measurements of high redshift galaxies and of planets around other stars that were never possible before, and we're making those measurements very precisely with instrumentation we don't understand. That's allowed. And so the fact that we don't understand the machine learning methods is not in itself a bad thing. It just means you have to use them in the right ways. And I'm going to make an argument about causal separations now for a few minutes, and then I'm done. So in astrophysics, we don't really do causal inference in the way that an astronomer, the way a statistician would say. But what I mean is we have data sets that there's multiple causes, and we want to separate those causes. So for instance, whenever we observe a star, we're observing the star through the atmosphere. And when we take I was warned, when we take a spectrum of the star through the atmosphere, there's features we observe, and most of them are from the star, but some of them are from the atmosphere. And we need to separate that out because we want to precisely measure the star. And I presume the same things exist with the things looking from space down at Earth, where you're looking at the oceans and there's things that are messing up your measurements of the oceans. I don't know anything about it, but I assume that there are. And when you're trying to separate out like what's the star and what's the atmosphere, and say I don't care about the atmosphere. If I don't care about the atmosphere, then I want to give my model for the atmosphere as much flexibility as I possibly can. So that, because I don't care about it, I want to get rid of it as well as I possibly can. And so there's a role for machine learning here, because you want a very flexible model to capture these things in your data that you don't care about. And it's also true for us in instrument calibration, in the sense that one of the things astronomers do, by the way, that's just ridiculous, nobody else in the world can understand why, is we measure the brightnesses of stars very accurately. Like literally a part in 10 to the 6, we're measuring the brightnesses of stars. The reason we do that is because sometimes a planet passes in front of the star, and we want to be able to see the tiny effect of a planet passing in front of the star. So we try to measure stars at 1 part in 10 to the 6. Well, I can tell you, no cameras have a stability of a part in 10 to the 6 ever. And so we have to figure out what's coming from the star and what's coming from the planet. And there's too much to describe in here, but we are trying to find effects in the data that are like a few hundred parts per million. And in the very best instrumentation we have, we get thousands of parts per million in the variation. And we have to build a model for why the camera is varying. And you can't see this because it's tiny and it's far away, but there's a green line through those data points, which is a machine learning model of what the Kepler spacecraft was doing while it was observing this star. And then when we take it out, we see, and these have very different scales. You see there's a factor of 10 in the scales. And one of the things that's embarrassing about this is a machine learning model of the Kepler spacecraft, and it turns out it's completely interpretable. I'm embarrassed to say, but it's an interrogation kind of interpretability, in the sense that each of these spikes that you see are thruster firings by the spacecraft. Every time it fires its thrusters, it changes slightly its orientation with respect to the star, which slightly changes the light path through the instrument. And note that connection engineering, machine learning methods are really useful in calibration of instruments, because they have a lot of capacity to capture all sorts of crazy things that you're, like this is a very high capacity model. By the way, this model was not trained on this star. This was a prediction for this star. so very high high fidelity, very featured predictions can be made by these models. That's why they're so valuable. Here's another example. This is like too much to explain, but it's this thing I mentioned before. This is a star that this is the black in my data. In my group, data are always black. Here's the data on a star. Some of the features in this spectrum come from the star and some come from the atmosphere. Here's the atmosphere. These are doublets that I think are due to rotational water transitions, but whatever. There's some absorption transmissions in the atmosphere. This is the star. Both this model and this model are just machine learning models that fit this data. But it can very clearly separate the atmosphere from the star. And the reason we can do that is we're on the Earth. We're observing, you observe down to the Earth. We observe out from the Earth. The Earth is a moving platform. So sometimes you're moving towards the star and sometimes you're moving away from the star. And so the star and the atmosphere get Doppler shifted with respect to each other. From those Doppler shifts, we can separate out the star from the atmosphere. But it only works because we have an incredibly flexible model for the atmosphere. And these tiny little features, I don't know if you can see them, there's tiny little deviations. Those turn out to be real deviations that people didn't know about before. We discovered a bunch of atmospheric absorption lines that weren't known about before. So I just want to make a comment related to those things, that it's usually considered like crazy. Oh, I'm going to just throw machine learning at it. Yay, let's throw machine learning at it. But actually, in these causal separations, machine learning can be the most conservative thing you can do because it gives the most flexibility to the part of the problem you don't care about. We didn't care what the spacecraft was doing in that case, so we just wanted to give it tons of flexibility. So that's actually the most conservative thing we could do. Good. Now, what I'm interested in the long run, and I think it's very relevant to, it's super relevant to us in astronomy, I think it's very relevant here too, is how do we increase trust in these emulators or these surrogate models? We need to trust them because realistically we need them. We just can't do enough simulations to solve the problems we want. Besides which, we should be reducing, not increasing our carbon footprints in our research. So we need to figure out a way to build trust. And I have various approaches, but I don't have a solution to this problem yet. We're looking at exact symmetries, and I'll show you an exact symmetry thing in a second. We're exploring things that relate to adversarial training. Like if you're concerned about certain kinds of adversarial modes that might appear, you can attack while you're training so that you're safe to those. We're thinking about sparse resimulations. Like if you're training something, could you check that the training is staying on the rails by doing sparse resimulations? I don't know. We haven't figured that out yet. That's all stuff I'm talking about with Soledad Villar. And did I put one in? Yeah, just a comment. This is, I was talking right before the talk with Vivi about this. Say you are emulating something, you're doing a surrogate model, and you believe that the relationship that you're trying to get is invariant or equivariant. So in cosmology, we believe that the laws of physics are independent of translation, independent of rotation, and independent of time. And those symmetries have to be there. And you can think of those as like group operators. Like you can rotate the initial conditions and rotate the output, and it should be the same answer. And that is an the mathematicians call that equivariance to a group. So if something is invariant or equivariant, physicists call that symmetry and mathematicians call that equivariance. If you know that's true, then we can take the predictions of your model and we can provably improve them by doing an operation called group averaging, which is a way to symmetrize your output answer. So if you're simulating the differential equations of the oceans and you have an emulator for it and you're not totally happy with it, we can make it better, and provably our version will be better because the differential equations that govern the ocean are in fact equivariant to lots of group operators. This will not solve all your problems, I can assure you. That doesn't solve all, but the nice thing is you can do this no matter what your model is. We can take it after you're trained it and improve it. And we just wrote a little paper about this that we haven't put on the archive yet, partly because Soledad points out that there's nothing new in this paper. We're just applying something that's already known in math. So there's a battle. She's saying Nothing is new in this paper. And I'm saying the physicists don't know this. And she's like, but there's nothing new. Anyway, you can imagine what our Zoom calls are like. Good, this is it. That's all I said. Machine learning tools can be dangerous and they produce biased outcomes, but they're in contexts in which you need machine learning, either for computational reasons or for intellectual reasons like these causal separations. Thank you.
Thank you so much, David. Would love to hear questions. Would anybody in the room like to kick us off?
Hello, my name is Ishaq Isa. I'm an architecture designer. Just based to where you say for machine learning, and the question is, I'm not sure if you can answer in a short answer, but is the satellite, for example, James Webb satellite, is a do they use machine learning in the satellites?
Great question. There's a lot of discussion about where, like, so so many things to say. The satellites that need to be very cold, like James Webb, are at L2, so they're not in low Earth orbit near the Earth. They're way far from the Earth, and that means to communicate back with the Earth, they go through the deep space network. You can't just directly broadcast to a normal antenna that like are used in the Earth sciences. We have to use a special set of antennas that can go to very large distance. That means they're all bandwidth limited, which means the satellites make a ton of decisions on board about what to downlink. They don't downlink everything. They make a lot of decisions. Right now, all of those decisions are made by expert systems where we decide in advance, like at whiteboards, like what are going to be the cuts that say that this piece of data should go down and this piece of data shouldn't go down. But we are inches away. I'm sure that the next generation of projects will have like machine learning classifiers on them and be sending down the data that are either anomalous in an interesting way or not anomalous or fit with something. I'm sure that's coming. But right now, they are very much expert systems and not like machine learning systems.
Hi. Can you speak more to the difference between interpretability and interrogation of a machine learning method?
Right. So the early ideas, so this is a bit of a cartoon because I don't work in this area, but my cartoon of it is that the original idea of interpretation is you just look inside and it would make sense. So for instance, in PCA, when you do PCA, you get these eigenvectors. And if you're doing PCA on a set of like, I don't know, spectra of parts of the ocean or whatever, you'll find that they're interpretable as, oh, there's the oxygenation. Oh, that's the amount of algae in it or whatever. The PCA components sort of seem interpretable, but once the machine learning methods got more capacity, there was just no way you could just project out something internally and just see the effect or figure out what it's doing. So that kind of ended. And now the new kind of interpretability that people are working on is more like you hobble it and ask, how does it perform when you hobble? Like you hide part of the data and ask, was this part of the data necessary for it to make the, so you sort of run experiment, you almost treat it like a lab subject and you run experiments on it and use that. So when people say, oh, transformers are interpretable, you can see these attention maps or whatever. That is basically an interrogation, like it's an end-to-end interrogation. You're not looking inside the transformer, you're running data through the transformer to find the attention maps. So that's what I'm thinking of as like interrogation. And of course, in ChatGPT and things like that, people are literally trying to understand what ChatGPT is doing by talking to ChatGPT. Which, I don't know if that's a good idea.
Great talk. I very much enjoyed that. Very aligned with a lot of things we are thinking about, and I very much liked your point, especially on what we learned, right? And I think we've not been pushing as much as maybe we should in terms of what we are learning using those tools, as opposed to the prediction component. Maybe there's one thing I didn't really understand. I think it's also because we are coming from a different perspective, in terms of the causal inference. Where we are coming from is that we actually need some sort of causal reasoning because if you think, for instance, about climate change, right? I mean, you want to do like some sort of counterfactual, like a what if question. That's actually very fundamental. And that's where you can see a lot of pitfalls in weather models when people saying it drives me nuts, to be frank, when people say, oh, I have a digital twin of the Earth because I was able to emulate like some weather at some point, right? That's just wrong, right? And we know that, and we can actually easily prove that. And just wanted to, and it was actually nice because then you actually kind of link those two pieces, and the emulation part. So just curious how you're thinking about that, like causality, and why you're saying that machine learning is useful for causality. So
good.
that's the piece I didn't read.
Good. My position is very limited. By the way, I really like that you mentioned counterfactuals, because really a lot of science. There's a weird thing about astrophysics, especially cosmology, because cosmology is like unitary evolution of the universe from initial conditions. So there is no counterfactual. It's like literally unitary. There's no free will. You can't do an experiment. You can't make a different. You can't change part of the universe and see what happens. So there is no counterfactual, and yet almost everything we ask in science is a counterfactual form. We're like, oh, if this galaxy had not had, like if the Sagittarius dwarf wasn't crashing into the Milky Way, it would be different. Well, that you can't have that counterfactual. So that I'm glad you, and I think it's very interesting to think about Earth science, because the counterfactuals are the most important thing. The place that machine learning, it's hard to find a very good simple example, but roughly speaking, it's, I think of it much more in the social sciences. Actually, I learned all this from the social sciences. In the social sciences, you're asking, like, these children are doing worse in school than these children. Why? Is it because like the policing is worse in this neighborhood? Is it because of poverty? Is it because of malnutrition? Like, you have all these things. And say you want to write a really sharp thing about policing. You can only write a sharp thing about policing if you give a ton of flexibility to the nutrition and poverty model. So you have to allow nutrition and poverty to do a lot of things, because otherwise, if you oversimplified what can be happening in that sector, it might, the remaining residuals might get projected onto policing. So that's why it does have this conservatism. If you're trying to ask a sharp question, so in astrophysics, we're always trying to ask a sharp question. Like with those two spectra, we're actually trying to find the velocity of the star very accurately. So the shape of the stellar spectrum, don't care. Shape of the telluric spectrum, don't care. All I care about is the relative velocity of the two components extremely accurately. And to do that as conservatively as possible, I have to put as much flexibility as I can into those two models.
Yeah,
Does that help?
It's more like a data flexibility, maybe more than the model itself.
Exactly. It's not really the model, it's the flexibility. Exactly.
Exactly.
Very good. Yeah.
And the just sorry, taking long here, but the example I always give is that you can look at global air temperature, and you can have CO2 on the x-axis. You could have years. You could have population. You can have like a bunch of stuff, right?
Yeah.
Like urbanization, and they are correlated, right?
Yeah, of course. Right. And so if you want to ask a sharp question about whether it really is population that's melting the glaciers or whatever, then you need to put a lot of flexibility into all the other parts to make sure that it really is population that's doing it. Yeah.
So another way of saying that is that the null result is that like poverty explains everything, basically.
Right. Exactly.
If you
Yeah.
can't explain everything with poverty, then your model will do that, and it won't have anything left for sort of the policing.
That's right. It's a way to make your null more flexible.
Yeah. Okay, that wasn't my question though. So just on the emulation, and also this idea of like ML being good at engineering. I mean, I know you work with like MCMC and stuff like that. So like we've done things like using ML just as a step to do MCMC faster.
Yes, exactly. Yes.
We throw away our machine learning model and wash our hands and go back to
good. Yeah. Yes, sometimes that's a very good example. Machine learning can often be used to aid a search like MCMC, but also think about the AlphaFold. It can give you suggestions of what drugs to try. Of course, at the end of the day, the successful drugs will be the ones that actually satisfy trials, real trials, but it might really speed your approach to that. Good, very good. That's very good use. Yeah.
The other thing is that I remember a friend of mine once told me after I wrote a paper that it was a good paper, but that was a bad thing because people would copy it poorly. And he said, instead, you should write a bad paper, and then people get angry and they do good science, refute your bad science.
Yeah, good, yeah.
This could be a potential role for a machine learning.
Really, it could be. And I have to say, one of the reasons this is a little bit embarrassing, but literally one of the reasons I insisted that we write this good or bad for science paper with Soledad, who, as I told you, was uncomfortable about it, is that people are looking to cite things when they're uncomfortable about machine learning methods, and they're looking for a language for making criticism. So we did actually partly do it to give people a language and a context for criticism. But yeah.
Olia, would you like to unmute and ask your question?
Yeah, thank you very much, and thank you for the great talk. I really like philosophical talks on machine learning. It's less of a question, it's more of a comment. I'm not sure I can understand fully your example that you were giving with the biases, but it reminded me of something that was presented at the conference last year. So I just added a paper. Basically, they talk about this inherent feature of neural networks that they have this spectral bias.
Yeah.
In training, and they propose to just solve it with regularized root mean square errors, basically to avoid this bias. So I don't know if that's relatable to what you showed.
It is relatable. Well, actually, there's been quite a bit of work on this kind of bias, and there's recently a paper in the astrophysics community, which is like called something like machine learning regressions always underestimate the extremes or something like that. It can be partly mitigated by cost functions and regularizations for sure, but not ever completely. And I think it really is because if you're at the think of the way I think about it is that all machine learning methods are fundamentally nearest neighbor methods. They're always trying to find neighbors, and all the sophistication of machine learning is always about like being very clever about what your neighbors are. So that means if you're an extreme example, if you're way out to the left, almost all your neighbors will be slightly to the right of you. And so the average of your neighbors will always be to the right of you. And it really comes back to the original definition of the word regression. Like really, the word regression was like coined to be regression to the mean. And it's just that the mean is made more sophisticated by the fact that you have all this other data. But I think it is actually very interesting. In any individual application, I think you can both mitigate the bias and also try to estimate the bias by various things. But I don't think you can ever fully get rid of it. That's my point of view, but I might be wrong. I mean, I'm interested if I'm wrong. As I said, I think there's an approach that relates to likelihood functions that might get away with it, get around it. I'm trying to figure that out now.
Thanks for the awesome talk. I just wanted to understand from your domain expertise, like when you have the problem of missing data in your concerned area, it's like it's very difficult to, would say, fill that gap which comes with that missing data, and you never know what is correct, what is not correct, and even the smallest wrong thing can derail every parts of your project. So how do you deal with it?
Great. I love this question. I could give a totally separate seminar about like how you deal with missing and corrupted data, because of course there's one of the things that's very irritating about when I opened with like, what is machine learning? Almost all of these methods require rectangular data that's complete and cool. You know, and in fact, one of the reasons that transformers took off is they take ragged data, but almost everything else here requires like complete, reliable, rectangular data. And I have never had a data set that's complete and reliable and rectangular ever. So in some sense, none of these are ever useful. And actually, a lot of my research is about how you deal with missing data. And most of the good approaches for missing data, I think, involve sort of punking these models into models that are more generative, that generate your data, because then you can use the generative side to fill in at the same time that you're using the discriminative side to make decisions. So most of the things we do with corrupted data involve building like sort of a two-armed thing that is both generative and discriminative at the same time. So you can generate the fake data. And then you can also generate the missing data. And you could also, by the way, then classify every pixel of your data set as possibly corrupted. Well, I love that. I really like it when my machine learning method runs, gives me good answers, and also says, I think these data points are corrupted. And that's a big thing that we work on in my group, because we are working with real data and it's always corrupt. But I think that it's very problem specific, of course, and but I think it's such an important area. And that's one of the reasons why these absolutely vanilla methods are rarely useful right out of the box. Like many people have probably had the thing where you run PCA and then it's all dominated by some outlier. We get this all the time. One cosmic ray hit one spectrum, and then all the PCA components have a big block, a big feature at this exactly the same location. Yeah, good. I think that's the most important thing in some ways in all of machine learning.
Thank you.